Hello. So we are going to continue our discussion on binomial distribution. In the previous two videos, I introduced binary distribution. So that was just a preliminary knowledge. So we need that knowledge to study the full binomial distribution. So let me compare that. So what we learned, what we studied in binary random variable is like choosing a random answer to one multiple choice question. So from one question, the outcome is either correct or wrong or correct. And then, we are going to extend the problem. Instead of considering one question, we will consider one quiz, which consists of 10 questions. And you are randomizing your answers to all of the questions. So then what we are interested in is the number of correct answers, right? So like if you are super lucky, you can get 10 points. It is theoretically possible. Probability is not zero. If you randomly choose answers and if all of them are correct, you can get 10 points. But you can also get zero, right? If you are very unlucky, all your choices were 0 points. Actually, before the COVID-19, I had final exam, like midterm final exams with 20 multiple choice questions. 20 multiple choice questions, and I saw a student who got 0 point. 0 point out of 20. So chose all wrong answers throughout 20 questions. I was surprised. How can that be possible? So anyhow, that kind of distribution is the binomial distribution. So in this chapter, I will denote one single variable, one single binary random variable as x. It is either correct or wrong, a single question, but y is the overall quiz grade, which counts the number of correct answers out of n experiments. So experiments is a quiz, right? So it can be an integer between 0 and n. So if you choose all wrong answers, your grade will be 0. If you all choose correct answers, then your grade will be n, which is like the number of questions. Okay. Here I'm going to add more assumptions. It is more complicated structure, so we need more assumptions. So first, we assume that there are n trials of binary experiments, right? One question is one experiment. You are randomizing question by question, and in each question on each trial, there are only two possible outcomes. So basically, same assumption, and the probability of success is p, all right, following the binary distribution assumption. And finally, actually, this is more important, hidden but most important, those experiments are statistically independent. We learned statistical independence in chapter 2. I said it is very important at the time, like I told you, independence is a very important concept in statistics. We are going to use it, and it comes again soon. So anyhow, under these four assumptions, we will call our random variable y as a binomial distribution with parameter n and p. So here you need two parameters. To describe this distribution, you need to specify the number of questions and the probability of correct answer for each question. And all the questions must have the same probability, and they are independent. That is, they are these two parameters. So you are summarizing the full distribution with two parameters. If you know these two parameters, you can calculate anything, right? This is the example we have considered so far. So in our example, like the binary case is actually one special binomial distribution. So let's say xi is the result for question I. And if you choose correct answer at question I, you get 1 point, otherwise 0. And probability is 20%. And what you get is, what you are actually interested in is not just single question, but overall grade out of 10 questions. So sum the result through 10 questions, and then your possible outcomes are 0 to 10. Possible grades are 0 to 10, and then you can say that y is a binomial distribution with parameter n and p. N equals 10, p equals 0.2, right? So imagine the situation, the assumptions, what we are studying. Okay, then now let's think about another example. We are going to study this example from the simplest to the more general case. So we will assume that there are 10 reservations for a flight, or you can imagine for a restaurant or for a hotel. So 10 reservations are made. And for each reservation, it can be canceled. A reservation may be canceled with 10% probability, right? So possible. And I'll additionally assume that cancellation is statistically independent. So even if one passenger canceled his or her reservation, it has no effect on the other passengers, right? A table in a restaurant is canceled, but it does not change the probability of cancellation to the other tables. Okay, and then now under this setup, for each reservation, the outcome is binary because the outcome is either canceled or not canceled. That's the only possible outcomes. And we are going to denote cancellation as success. So I said success doesn't necessarily mean something good. So I will just call cancellation as success because that is the event we are interested in. So we are counting success. We are interested in probability of success. How many cancel? I mean, we are interested in how many cancellations can happen. Probability of cancellations. So we are going to call cancellation as success because we are interested in that. So 1 if cancelled, 0 if not. That is our notation. So y is the total number of cancellations out of 10 reservations, right? There are 10 tables, reserved tables, then actually how many of them are going to be cancelled? We can parameterize the distribution with n equals 10 and p equals 0.1. So you are good, you know the parameters, but what you don't know is any properties about binomial distribution. So now from now on, we are going to study the properties of a binomial distribution, which is quite complicated as you can expect. So I will start with brain teaser. So like exactly same situation. There are 10 reservations. Cancellation probability is 10%. And all cancellations are independent. And then what is the probability that exactly 2 reservations are cancelled? Guess what? Using those numbers, there are only 3 numbers. 10 reservations, 10%, 2 reservations. Combine them and guess what is the probability. You cannot solve this right now, but we are going to come back this question at the end of this derivation. Just guess. You may think it is 20% because 10% should happen twice. Or you may think it's, let's say, 5% because 10% divided by 2, something like that. Let's see. The answer is E, 19.37%. Oh, can you imagine where this number came from? From these basic numbers? That's what's amazing about this distribution, right? So we are going to study why. That is an intermediate goal of this lecture. And to see that, we have to go through several steps. It is not easy to see the full mechanism in one step. So I will go step by step, and I, I do it in 6 different steps. So it is a process of generalization. We are going to study when their reservations are 2, when there are 3 reservations, when there are 4 reservations, and we will generalize from there. Okay, the first step is to understand independence. So, it's a review. Suppose that A and B are independent binary random variables. And then choose a incorrect statement. Choose an incorrect statement, not correct. Remember the definition or the properties of independence we learned in chapter 2. At that time, one of the first thing you can remember is when A and B are independent, basically conditional probability equals unconditional probability. So probability of A is not affected by the information about B. So A is correct. So unconditional probability of A equals the probability of A when B already happened. So they are same. That's the definition of independence. Similarly, C is the same intuition. Probability of A does not change even if B happened or not. Right? So C is the same thing. Finally, E is also the same thing. Unconditional probability and conditional probability not affected. So cross out A, C, E. And then another important property of independence is the special multiplication rule. Under independence, you can express the probability of intersection as the multiplication of 2 simple probabilities, right? So probability that A and B happen at the same time equals probability of A times probability of B. That was special multiplication rule, which is true only when 2 events are independent. Then the answer is D. D is incorrect. It is the special addition rule, which is true under mutual exclusiveness. So it is different. It is has nothing to do with independence. So D is the answer. What I want to say here is we are going to use this property. The special multiplication rule is what we are going to utilize. Okay? So, not just this simple multiplication rule, but it is not that difficult to see the relationship like when you have 3 events. So when you have 3 events, if you want to calculate the probability that A and B and C happen at the same time, then this probability must be the multiplication of 3 simple probabilities. Direct, straightforward extension of 2 events case. So even if you have more events, like say A, B, C, D, E, F, G happen at the same time, right? That probability is multiplication of simple probabilities as long as they are independent. So I will use this property when I have more than 2 events. So that is why we need this independence assumption. Okay, then second step. I will consider the case where there are 2 reservations. Our question had 10 reservations. which is very complicated. So let's start with only 2 reservations. So it is much simpler. So assume that there are 2 passengers, A and B, who made reservations for a flight. And probability of cancellation is 10% for each of them. And A and B do not know each other. They don't know each other, so they are independent. Their cancellation decision is independent. In this case, what is the probability that A cancels his reservation, but B doesn't? Think about this. Okay. Let me turn to the next page. So, what we want to calculate is this event. I said A cancels. So, A should be 1. A equals 1. And B does not cancel, so B equals 0. And then, in the end, we want to calculate probability that A equals 1 and B equals 0. But we know these two are independent, so we will be calculating multiplication of them using the special multiplication rule. So we know that the probability that A cancels her reservation is 10%, and the probability that B does not cancel her reservation is 90%. So it is obvious. And then we get the probability of the intersection as a multiplication. That is 9%. You get it? So in this sentence, I'm requiring 2 conditions happen at the same time. A's cancellation and B's non-cancellation. And this is 10%, this is 90%. You multiply them. That is the answer. The answer is C. 9% is the answer. Okay? So then, basically, so this is why 2 reservation case is simple. Now I'm going to define the binomial distribution like this. Y is the number of cancellations. And we still consider 2 reservation case. And same thing, everything is same. 10% cancellation probability and independence across reservations. And then, can you answer this question? What is the probability that only one of these 2 reservations is canceled? Exactly one of these 2 reservations is canceled. Calculate, try to guess the probability. You learned how to calculate this event, right? Because we just learned that the probability that A cancels but B does not equals 9%. So you may think the answer is C. The correct answer is 18%. Let me explain why. Why it is 18%, not 9%. That's because there are 4 possible outcomes. Each reservation has 2 possible outcomes. So, like combining 2 reservations, there are 2 by 2 possible outcomes. Okay? And among these, I am asking you, what is the probability that exactly 1 reservation is canceled? Exactly 1 reservation is canceled includes these 2 events. So, we calculated this probability, this outcome has 9% probability, right? But 9% does not include this side. So this is 9%, and this outcome is also 9% because they are symmetric, right? So in the same way, this must be 9%, this must be 9%. So like the probability of 1 cancellation is 9 plus 9, 18%. That is how you calculate that probability. So what the trick was that you have to think about all possible cases. So when I say 1 reservation is canceled, it could be A who cancels the reservation, or it could be B, right? So there are two possible scenarios. You have to consider both cases. So the probability is double of a single probability, single scenario, right? And another important point here is basically this and that. When there are like so, either A cancels or B cancels, probability must be the same because everything is independent and all the probabilities of cancellation the same. So what matters is counting the number of cases. So then, now I'm going to generalize this one more step. So y is the number of cancellations. And I will assume that there are 3 reservations, one step further, and probability of cancellation is the same 10%, independence is the same. In this case, out of 3 reservations, what is the probability that exactly 1 reservation is cancelled? Oh, if you're smart, you may be able to answer this question, but still it can be quite difficult. Try this. I'll give you more time. I'm going to finish this video here, and I will explain that in the next video. Try this. It'll be fun. See you later.